Hello, everybody. I hope you're all doing well. So, for today, we're going to be solving a problem where we will use the method of joins in conjunction with the method of sections. So, we'll use them together on the same problem. Okay. So, here is the problem for today. So, I already have the figure drawn here. Okay. So, in this particular problem, we need to find the forces in the following bars. Okay. So, find the forces in the following bars, which is bar CD, then the bar CF, the bar GF, the bar AB, AH, and the bar DF. And then the idea is we have to state whether they are in tension or in compression. Okay, and then state whether they are in tension or in compression. All right, and the main reason for using the method of sections is that sometimes we don't want to find the forces in all the bars of a truss. Perhaps the designer knows, or we have information that okay, there are certain bars that are more prone to failure than certain other bars of a truss, and so our aim is to analyze only those bars. And so if we need to do only a few force analyses on the truss, then there is no point in doing the method of joins and starting to look at each and every one of those bars, okay, because that is not useful to our problem. So in that sense, the method of sections and the method of joins can be used together. Okay. All right. So this is the problem that we need to solve. Before I start solving this, I just want to write down some key ideas. Okay. So key ideas, and these are the following. Method of joins and method of sections can be used in conjunction on the same problem. Okay, so method of joins and method of sections can be used in combination on the same problem. Okay. Then, method of section can be used multiple times on the same problem. Okay. Method of sections can be used multiple times on the same problem. And my multiple doesn't look like it makes sense, so let me rewrite it again. All right, sorry. Can be used multiple times in the same problem, but every time I use the method of sections, I have to perform a new cut. Okay, with a new cut performed every time, and you'll see this in this particular problem. The third thing that I have mentioned in my earlier video on method of sections, do not cut through or section through more than 3 bars at a time. Okay, so method of sections okay, so do not cut or section through more than 3 unknown bars at a time. Okay, and a couple more points. We should always be in a position to find support reactions. Okay, so can find support reactions if needed. More or less, most of the times, 90% of the times, if you're solving a problem using method of sections, chances are you need to find a support reaction. Okay, and then my last point is always assume each bar to be in tension to begin with. Okay, so this is what we need to do, and these are the important points that I typically follow whenever I solve a problem on method of sections and joints together. So I go back to my problem here. I'll quickly look at my figure, okay? And I notice that I actually need to have some slope triangles here because there seem to be a couple of angles that I'm not too happy about, but we got to do what we got to do, right? So that's one thing I need to do. The other thing I need to do is I look at the support at E. That's a roller, okay? Let's write this down. So this is a roller support, okay? And then this is a pin support at A, which means that in total I have 3 unknown reaction forces, right? 2 at the pin A and then 1 at the roller. And so I can find out what these reaction forces are by performing a rigid body equilibrium analysis of the truss itself. So let me do that, okay, to begin with, okay? So I'm going to copy all of this, bring it down below, and I'm going to find the support reactions, okay? So let's start off, and let's make a strategy here, okay? So what could be our strategy before we do anything further, okay? I look at the bars CD, CF, and GF. Okay, so maybe let me put a small tick mark. So this is CD, this is CF, and then this is GF, and then I have AB, which is sitting somewhere here. So this is AB, this is what I need. Then I need AH, and then I need a DF. Okay, so my strategy is I will pass a section through CD, CF, and GF, which means I'm passing a section through no more than 3 members of the truss. Okay, so my strategy is I will first cut through these 3. Okay, I will cut through these 3 so that the truss is broken into 2 clean pieces. Always imagine you're taking a piece of Kit Kat and then you are breaking it apart. When you're breaking it apart, you're breaking it into 2 clean, smooth pieces, okay? And so my strategy is I'm going to calculate CD, CF, and GF using the method of sections. And AB and AH, you can see obviously, I can draw the Venn diagram at A. I will be able to get AB and AH using the method of joints. DF, I can actually directly look at the figure and tell you the DF is going to be 5 kilonewtons in compression, and I'm pretty sure you can do that too. But you can use the method of joints for that. Okay, so this is my strategy. I'm going to get rid of the lines that I just drew here. Okay, so strategy. And typically when you start a problem on trusses, do not directly just jump in. Have a strategy, decide on what to do for what bars of the truss, and then go on and solve the problem. Okay, so I'm going to use the method of sections. To find the forces in the bars CD, CF, and then GF. Okay, then use the method of joints to find the forces on the bars AB and AH. Okay, so for this I need the pin free body diagram at A, and then the third is use method of joints to find the force in the bar DF. Okay, so this is by drawing the pin free body diagram at the point D. Okay, I've heard many people call this as force body diagrams. That's not the right terminology. These are free body diagrams. When you say free for anything, it means that you're taking the body and you're detaching it, or you're isolating it from everything that holds it in place, so that you draw it as a free body. It is unencumbered, it is unfettered. Okay, and then you start drawing the effect of the support and so on and so forth. All right, so that's my strategy for the day. Let me start off by finding the support reactions. Okay, let me also write that out. Okay, so start off by obtaining the support reactions at A and E. Okay, all right. So I think I already have my figure copied. I'm going to bring it down. Beautiful. Okay, so when I'm drawing the free body diagram, the thing that you know is I'm not going to be showing any of these things, right? I'm not going to be showing any of those things either. Okay, so I'm going to be cutting that off, and probably I don't need that either. So this is the situation that I have. Instead of showing the supports, I show the effect of the support at these different points. Okay, so in this case I'm going to have reaction forces at the pin A. Let me draw it, and I'm also going to have a reaction force at E. So I'm going to have a roller reaction which I'm going to point it upwards here. So I'm going to call it as EY. Then I'm going to have an AX and an AY. Okay, so let me call my AY this way, and then I'm going to have an AX at the pin. Okay, just want to make sure that this is acting at the pin. And one important thing is all these forces are acting at the pins. Okay, none of these forces are acting at the bars directly, but the effect of the forces on the pin is transferred to the different bars. Okay, all right. And I have my little coordinate frame which is set up here. This is the part of the problem where you need to be quick, okay, to find the support reactions and so on, because these are things that are fairly straightforward, and it comes through practice, of course. All right, so I'm going to do the force balance equations. I can directly find out that AX is equal to 0 if I sum forces in the X direction. AX is equal to 0. Then I sum forces in the Y direction. I automatically find out there are two unknowns, so I just sum moments about some point. Okay, so let me start summing moments about the point A. That is equal to 0. Okay, clockwise moments are negative, or counterclockwise moments are positive. Okay, I'm going to have EY times 5 plus 5 plus 5 plus 5, which is 20, and that's going to be counterclockwise. Then I'm going to have the 3 kilonewton force, which is acting at the point E. This is going to produce a clockwise moment about the point A. Then I'm going to have the 5 kilonewton force. All of them are going to produce clockwise moments. 5 times 15. Then I'm going to have 4 times 10. Okay, then I'm going to have one more, 4 times 5. And that's about it, right? Because all the other forces are sitting at the point A. Put together, this is equal to 0. Okay, solve for EY. EY is going to give me approximately 9.75 kilonewtons. Okay, so that is the end of EY. And once you have EY, some forces in the Y direction, set them equal to 0, all the forces pointing up being positive. What are my forces? I'm going to have AY pointing up, EY was pointing up, then I'm going to have minus 2, minus 4, minus 4, minus 5, minus 3 is equal to 0. And I can solve for AY. It's going to be 8.25 kilonewtons. Okay, so as I said, these are supposed to be the straightforward parts of the problem. Okay, so a good question check or a good knowledge check or an honesty checkpoint is if you are struggling with finding the support reactions for a truss, then you may want to go back and then practice more problems on rigid body equilibrium in 2 dimensions. Okay, it's the same basic idea being used for pretty much all the problems in statics. The bodies are in static equilibrium, which means that the sum of the moments at any arbitrary point is 0. The sum of forces at any arbitrary sum of forces in the X and the Y directions are 0, or in the orthogonal directions are 0. Okay, so this is the same thing that is being used for multiple different situations, as you are saying. Okay, so I'm done with the support reactions, and I'm going to grab my figure once again from here, because we are now going to make use of the method of sections. Okay, so if I go back to my checklist, If I very quickly go back to my checklist, I see that, okay, I start off by obtaining the support reactions. Okay, so this is done. Then the next step is I'm going to use a method of sections to find CD, CF, and GF. Or it's not necessary that I use a method of sections first. I can use the method of joints first as well. Okay, there is no necessity that I follow this particular order that I have written. It is just that a method of sections is more elegant. So I would like to get that done much before I do the method of joints. Okay, so this is my next strategy. So after that, I will do the method of sections to find this guy. I will use the method of sections to find this guy. It is not necessary that you follow through in this particular order, except that if you don't find the support reactions, you can't do anything else in this problem. Okay, so I would probably do this first. Okay, so that I would find the support reactions first. Okay, and then the rest of them you can either go ABC or BCA or CAB or whatever order you choose. Okay, so I'm going to move forward and I'm going to use the method of sections. Okay, this is to find the forces in the bars CD, CF, and then GF. Okay, so I'm going to put my figure down here. I have calculated the support reactions and so on. Maybe this is a good time to calculate my slope triangles in this situation. You can obviously see that the slope triangle attached here, let's see, slope triangle here. I have one slope triangle here which is necessary for me. Okay, I'm trying to draw a straight line. As you know, sometimes I'm not able to draw straight lines. All right, so this is going to be 5, and then this distance here is going to be, well, that is going to be 3, I'm sorry. This is going to be 3. This is going to be 5, okay? And if I draw a slope triangle here, then that's going to be a little tricky, but I hope you can see it. This is going to be 5, this is going to be 2. Okay, so which means that here this is going to be 25 and then 9, that is 34, and then this is going to be square root of 29. Okay, so my writing is a little small here, and I will keep the 29 separated out, or I can show you that the slope triangle on the other side is going to be 5, 2, and 29, so that I'm not cluttering my figure here. Okay, so I can show that this slope triangle here, which is going to be the same as the slope triangle I just wrote down for the other piece, this is going to be 2, this is going to be 5, and this is going to be square root of 29. Okay, and then this guy obviously was square root of 34. And what am I going to do now? I'm going to pass a section through the bars CD, CF, and GF. Okay, so here is my section. I'm cutting through these. I'm cutting through these in a nice clean manner. Okay, that is something that you have to see here, right? And then I'm breaking it up into 2 pieces. Okay, what are the 2 pieces? So I need to probably do the following. Okay, hopefully this gives me the 2 pieces that I need. So here is 1. All right, beautiful, I got it. So here is 1 piece. I'm just going to draw that right down here. Okay, so here is 1. I want to make sure that it's sitting right down there. Okay, that looks good to me. And then here is the other piece. Okay, got to be a little careful. And I got it. Usually I don't draw the 2 pieces in an exam or anything. I just draw it here so that I want to show it to you. Okay, and just for the sake of clarity, let me show this piece a little further away. Okay, I'm hoping that it doesn't seem to be aligned with each other, right? I just want to make sure that it's aligned with each other this way. Okay, beautiful. And I can also draw this section. If you want, I can copy this and then I can paste that here, showing that okay, this is how the section was cut. Okay, and obviously you can either look at the small piece or you can look at the bigger piece. My idea is, okay, let me look at the smaller piece, okay, so that my life is made a little easier. But nevertheless, I will show you the forces acting on both the pieces. Okay, so here I'm going to have a force. Because you're assuming it to be in a state of tension, the forces are always going to point away from the cut. Okay, so let's maybe write that statement down. Okay, so since the bars are in tension, the force at the cut on the bars will point away from the cut. Okay, so what I mean is, if I have a force on this bar CD, then this force is going to be pointing away from the direction of the cut. And since that is the case, I'm going to have a force which is going to be pointing this way. Okay, so this is going to be FCD, which means I'm going to have an equal and opposite FCD on here. I'm not sure how this creature sprang up on me, but as I see it, this is how it is. Okay, so this is going to be the force FCD. Then I'm going to have the force from FCF. Okay, this is also going to be pointing away from the cut, which means I'm just going to draw it out this way. Okay, and let me align it properly. So this is going to be FCF. And then lastly, I'm going to have and of course it's going to be having a force here as well, which you can draw. Okay, that's going to be FCF for me. Just want to make sure it's aligned well. Beautiful. Okay, so this is going to be FCF. And then lastly, I'm going to have this force FGF. Okay, and that's going to be pointing out this way. And that's going to be aligned with the bar GF, the direction of the bar GF. My hope is I can draw this out this way. And that doesn't look like it's aligned with the bar. Somehow these things are much harder to draw than drawing things by freehand, I tell you. Okay, that's really good. Then this is going to be F, GF, and likewise I'm going to have something right down here. Okay, that came out better. FGF. Okay, and then I'm going to have the slope triangles and so on, and your idea is you can either work on the piece which we'll call as section 1 here. Let me call this as section 1, or let me call this as section 2. Your choice is, you can either work with section 1 or section 2. So let me write that down here as well. Okay, can either work with section 1 or section 2. Okay, so that's one option that I have. I could do work on both the sections at the same time as well. That is also a possibility. Let me look at section 1. Okay, let me look at section 2, because it looks like the smaller of the two pieces. So that's something that I would do. Typically I would look at the smaller of the two pieces, because I would like to get this problem done with much more quickly. Right, so that's our whole aim here in this situation. Okay, so let me take section 2, and we know the support reactions at EY, which we just calculated earlier, as 9.75 kilonewtons. So work with section 2. And in an exam or in any kind of a homework assignment, it is not necessary for you to draw both the pieces. Okay, what I would typically do is I would just show you the cut, and then I would just draw the piece which I'm interested in working, which is section 2 here. Okay, so if I'm doing section 2, then here is what I have. I'm going to maybe increase the size of this figure so that I can I'm going to get rid of this guy, because I know that is the section I'm working with. I'm probably going to try and see if I can increase the size of this without increasing the size of my letters, but I guess that still is okay, or probably not okay. All right, so here is what I have. Maybe I'm not going to do that. I'll just leave it this way. Apologies. All right, and then I have a slope triangle. So this 3, 4, and 5 slope triangle is there for FCF. So which means that I'm going to take this FCF first of all, and then split it into its components. Okay, look at this very carefully. FCF and FCD, of course, they intersect at the point C. So if you want, you can call this as the point C. Let me keep it here. So if you want, you can call this as the point C where they are both intersecting. Okay, I can draw a dotted line if you want. Okay, so that is the point C. That is almost like a ghost point. Okay, that point is not found, but I can still draw a dotted line and say, okay, hey, that is the point where FCD and FCF are both intersecting each other. FGF doesn't do that. Okay, I want to make sure that this is aligned with this guy here. Okay, then FCF, I'm going to break it into its components. Okay, so starting from the point F, before I do that, let me take this guy and bring him down here. And I was trying to align this there. Sometimes it works, sometimes it doesn't. That's a little frustrating. That seems better. Okay, beautiful. FCF, I'm going to break it into components in the horizontal and the vertical direction. Okay, so that's going to be one component, and I'm going to have a component of FCF in the vertical direction as well. So the horizontal component is going to be 5 by square root of 34 FCF, and then I'm going to have this vertical component, which I can write down here. Okay, that's going to be 5 by, well, I was planning to write that down, 5 by, that's 5, that's 3, I'm sorry. So 3 by square root of 34 FCF. Okay, so that's one thing. Then FGF, I can take that and I can break it into its components. I have the slope triangle for this guy. If you recall, the slope triangle was 2, 5, and then the hypotenuse is going to be 29. Okay, square root of 29. So I can draw the component of this guy in this direction. I can draw a component of FGF in this direction as well. So this is going to be 2 by square root of 29 FGF, and then this is going to be 5 by square root of 29 FGF. Okay, so these are the components that I have, and the dimensions are also given to me in this particular problem here. Maybe I can extend these lines and then show you that, okay, these are this dimension of 2 is not actually necessary for me because I'm not interested in that. So maybe I can get rid of that. I don't need this one. I'm just going to make sure that this entire thing is gone. Okay, and let me bring this, and all right, so that's what we have. And since these are dimensions, we'll be drawing them in dotted lines. Okay, all right. Okay, and then distance of 5 meters, that's what I have here. So let me take this 5 meters and let me draw the dimensions in the following manner. Okay, so starting from the point C, this is FCD, which is supposed to be here. So starting from the point C, which is situated right there, okay, I'm going to draw the dimensions onto this force here. And then I'm also going to have the dimensions onto this particular force here. It's a hard thing to draw there, but I think we're successful. All right, and this is also going to be 5 meters. Okay, and I'm going to make sure that these are also in dotted lines. Appreciate your patience, bear with me while I have all the dimensions marked here. Okay, so that's going to be 5 meters, and that creature is also going to be 5 meters. All right, now we are ready to attack this particular section. Our aim, as always, is to solve these problems as fast as we can, right? So what is the strategy here? I need to find FCD, I need to find FGF, and then FCF. One strategy I can employ is I can sum moments about the point F. If I do that, then FGF and FCF both will not contribute to the moments. I'll be able to find FCD. Okay, so look at this. I'm going to sum moments about the point F and set that equal to 0. Counterclockwise moments are positive. And if you want, we have already drawn this figure at the beginning of the problem, so we don't need to keep doing it again and again, but it doesn't help. It doesn't hurt. I'm sorry. All right. So a moment about the point F is 0. So I'm going to have FCD. Use the right-hand rule. Distance of 3 meters. It's going to cause a counterclockwise rotation about the point F. Then I'm going to have EY. Don't forget EY. EY times the distance of 5. That's also going to be counterclockwise. And then I'm going to have this 3 kilonewton force which is acting vertically down, and that's going to cause a clockwise rotation. And that's about it, right? Because all the other forces are sitting there. This whole bunch of forces, if you look at FCF component, FGF components, all of them are sitting there. This 5 kilonewton force is passing through the point F, so that is not going to cause any rotations as well there. So if I solve, I get FCD to be in a state of compression, minus 11.25 kilonewtons. Something that I have told you in the past is do not change the direction of these forces in the middle of the problem. Okay, that is not a good thing. All right, so I found out one of these. I'm going to grab my figure again and come down to the second page, or the next page down here, okay, so that we can continue this problem. Another thing I can do, because my aim is to solve this problem quickly, another thing I can do is I can sum moments about the point C. Okay, if I sum moments about the point C and then if I set that equal to 0, then here is what I'll find out. FCD and FCF are sitting at the point C, which means they're not going to be causing any rotations about that particular point, which means that the only forces that are going to cause a rotation about the point C, or a moment about the point C, is FGF, and then the 3 kilonewton force, the EY, and then the 5 kilonewton force. Okay, so let's write this down. First of all, the horizontal component of GF, that's going to be 5 by root 29 FGF, and multiplied by a distance of 5 meters, all the way 3 meters, all the way to the point C. This is going to be a clockwise rotation. Then I'm going to look at the 2 by 29 root 29 FGF force. If I look at the distance from point F to point C, that's a distance of 5 meters. This is also going to cause a clockwise rotation about the point C. And then how about the rest of them? Okay, I'm going to have EY times a distance of 10 meters. That is going to be counterclockwise. Then I'm going to have the 3 kilonewton force, which is going to cause a clockwise rotation. So 3 times 10. And then I'm going to have the 5 kilonewton force, which is acting at the point D. That's going to cause a clockwise rotation about the point C. So that's going to be 5 times 5. And all of these put together is equal to 0. Okay, which means that I can solve for FGF in this particular situation. Okay, so FGF is going to end up being the following. So after solving for FGF, I get this to be approximately 9.1 kilonewtons. I get a positive value, which means that this tells me the force is in tension, or this bar is in a state of tension. Okay. All right. So I hope this strategy was fair enough to you. The other way you can always do, or another way is the following. Another way is you just write down all the sum of the forces in the x direction. Okay, set that equal to 0. What are the forces in the x direction? That's going to be, well, I have several of them here, right? I have FCD pointing this way, minus FCD. Then I'm going to have minus 5 by root 34 FCF, minus 5 by root 29 FGF, and that should be all the forces. That's equal to 0. I could call this as equation 1. Then I can say, okay, hey, sum of forces in the y direction is equal to 0. All the forces pointing up are positive. What are the forces in the y direction? I'm going to have 3 by root 34 FCF pointing up and EY pointing up. So EY 3 by root 34 FCF, and then this force of minus 5 minus 3 minus 2 by root 29 FGF is equal to 0. Okay, which means that you can solve this as a set of equations. Okay, you can use the method of substitution, or solve this as a system of equations, to find FCF and FGF. Okay, or if you have already found out FGF, by summing moments about C, then we just need to use equation 1 or 2 to find FCF. And you see, this is obviously much easier than solving a system of equations. When I solve a system of equations, I'm pretty sure I'm going to make a mistake. Okay, so once I do that, so using either of these two ways, I will obtain FCF to be the following. Okay, so that's approximately 3.2 kilonewtons, and that's a positive value as well, which means that this is in a state of tension. I'll write my results eventually. Okay, so this is the method of sections that was applied to this particular problem. Once again, very quickly, a recap of this method is that I have this bar here, and I'm going to find forces in CD, CF, and GF. I pass a section through all the three of them. I break it into two clean pieces. Okay, imagine breaking a piece of Kit Kat. Then I can either work with one piece or the other. I write down the forces on both the pieces. My forces are always pointing away from the cut. Okay, which is because I'm assuming all the bars to be in a state of tension. Once I do that, I can choose which cut I want to work with. I'm going to work with section 2 here. I can sum moments about the point F, and I can find out FCD. And I can also sum moments about the point C to find FGF. Look at the way I have broken the force FGF into its components, starting from the point of application of that force, okay, all the way to the point F here. Do not break this force into components in mid-air, okay? So this is what I've done here. Or you can solve this as a system of equations. You can find out FCF and GF this way. Either one is better. Either one is okay with me, okay? It's your choice. Okay, then I come to the next part of the problem, which is the method of joints at the pin A. Okay, so method of joints at the pin A, right? Because we had to find AB and AH. So that's fairly straightforward, as you can see. I can bring my figure from above here. We had this creature here, okay? So let me bring that down here. So copy that. Sorry to make your head spin by going up and down quickly. All right. So if I draw the pin free body diagram at the point A, what do I have? Okay. So here is first of all the pin. So this is pin A. Then what are the forces I have? The forces I have are AY, which is pointing up. AX is 0, so I don't need to worry about AX. Okay, so this was equal to 0 anyways. Then I'm going to have FAB, which is going to be pointing to the right, pulling on the pin because I'm assuming the bars to be in tension. Okay, and then I'm going to have FAH, which is going to be pointing this particular way. So this is FAH, and then of course I can also have my slope triangle for this bar point here. So that's going to be 5, 3, and root 34, as you know from before. Okay, so if I write this out, this is going to be 5, 3, and square root of 34. So I can break this into components along the vertical and the horizontal. So let me do that very quickly. Okay, so I'm going to have one component of this force in this particular direction. This is going to be 5 by root 34 FAH, Then I'm going to have another component of that force in the vertical direction. This is going to be 3 by root 34 FAH. And do not forget the fact that there is actually an applied force of 2 kilonewtons acting at the pin A. Okay, so there is a force of 2 kilonewtons which is acting at the pin A, and then AY, I think we obtained it to be approximately 8.25 kilonewtons. And so these are the forces acting here. This is the free body diagram of pin A. Okay, and I can start off by summing forces in the vertical direction. I'll find out FAH, then I'll sum forces in the horizontal direction. Okay, so let's do this. So sum of forces in the vertical direction, I first set that equal to 0. My coordinate frame for this pin, as you can see, will be my regular x and y directions. Okay, so this is y, this is x, and then this is positive. So forces in the y direction set equal to 0. I'm going to have AY minus 2 minus 3 by root 34 FAH is equal to 0. Okay, which means that I can solve for FAH, and if you do the math, this is going to end up being a positive value of 12.2 kilonewtons, which means that this is in a state of tension. And then I have to sum forces in the horizontal direction. Sum of forces in the x direction is equal to 0. What are my forces? I'm going to have FAB, and then I'm going to have 5 by root 34 FAH. Both of them put together is equal to 0, which obviously tells you that since AH is in tension, AB is going to be in a state of compression. So minus 10.4 kilonewtons. Okay, so that's done there. Then I also need to use the method of joints to find the force in the bar DF. I'm just going to scoot up and then show you so that you see this. So method of joints at A, and then I'm also going to use the method of joints at the pin at D. Okay, so that's what I'm going to be doing. So if I draw the pin diagram at D, I have DC, DE, DF, and then the 5 kilonewton force. Okay, so pin free body diagram. Okay, so this is what I have. I have the pin D. Then what are the forces on this particular pin? I'm going to have a force this way. I'm going to have a force this way. I'm going to have a force this way. And then I also have an applied force which is acting down here. I'm going to start labeling them. So this is going to be DC, DE, and then DF. Okay, so F, DF, F. I'm sorry, this is DE. This is FDE. Apologies. This is FDF. This is FCD or DC. Doesn't make a difference to our lives. And then this is supposed to be 5 kilonewtons. Okay. And you can very obviously see that I can choose the same XY coordinate frame as I have chosen for that particular pin here. So no harm done. And if I sum forces in the vertical direction and set that equal to 0, okay, then I will end up having the following: minus 5 minus FDF is equal to 0. Okay, so that FDF will end up being minus 5 kilonewtons. And you can also see that since I already know CD, I haven't calculated, I did calculate CD, so I could sum if needed. I mean, it's not needed in the problem, nobody asked me, but if needed, F forces in the x direction is equal to 0. I'm going to have minus FCD plus FDE is equal to 0. So obviously FDE is equal to FCD, and FCD we had obtained as minus 11.25. So FDE is equal to FCD is equal to minus 11.25 kilonewtons. This is not needed, this is not asked in the problem, but I'm just writing it out here. And then eventually I write out all my answers. Okay, so my answers are the following. Alright, so I start off by writing FCD. FCD was minus 11.25 kilonewtons, which means that FCD is going to be 11.25 kilonewtons in compression. Okay, then I'm going to have my other two culprits, FGF, which ended up being 9.14 kilonewtons, which means that this was a positive value. So FGF is 9.14 kilonewtons in tension, and then FCF ended up being 3.2 kilonewtons positive as well. Okay, which implies that FCF was 3.2 kilonewtons in a state of tension. Then I had FAB, as we just solved here, was minus 10.4, which implies that FAB was 10.4 kilonewtons in a state of compression. Let me scoot up all of these things so that I can finish off this problem within this particular page. I have two more things to write down. Okay, so I think that should be sufficient space. Then I had FAH, which I had obtained as, if I go back up, 12.2 kilonewtons positive, so that's in tension, so I'm just going to write that here, 12.2 kilonewtons in tension. And then FDF was minus 5 kilonewtons, which implies that FDF was 5 kilonewtons in compression. Okay, so that is important that you write down what these things are, whether they're in tension or in compression. Okay, and the reasoning behind this is so that if you're a designer, then it'll be much easier for you and much quicker for you to figure out, okay, what are the bars in tension, what are the bars in compression. If you're using different types of materials for these bars, then some bars behave different in tension and versus compression. For example, if you're using brittle materials, their behavior in tension is not the same as their behavior in compression. Okay, so that's something that one has to keep an eye out on, and that's why it is reasonable to have these written down. All right. So this was a fantastic problem. Very, very briefly, let me go over the problem details once again. Okay. So here is the truss. I had a pin support, I had a roller. I needed to find the forces in the bars CD. Okay, if I want to put a tick mark, CD, CF, GF, then the bar AB, the bar AH, and the bar DF. And my strategy was to use the combination of method of joints and the method of sections. Okay, if I use the method of sections to find the forces in CD, CF, and GF, right? We wrote down our strategy right down here. Then I use the method of joints to find AB and AH by drawing the pin free body diagram at A. Likewise, I do something similar at the pin D. And then, but before I do all of these things, I need to obtain the support reactions, which is what I did here. Pin at A, roller support at E. So EY, AX, and AY, sum of forces, sum of moments. That should get you going. Once I do this, then I come back and I cut through, break it into two clean pieces. If you want to make multiple pieces, that is completely fine, but you got to do it new every time. Okay, you got to do it new every time. So for example, in the same problem, if I were to find the force in BC, CH, and GH, what I would do is I would do a new cut. Okay, I would have done all of these things, then I would come back and then I would do another cut at BC, CH, and then BH. Okay, so then after this I can either work with section 1 or section 2. I'll work with section 2. Okay, and then I can find out the sum of forces, sum of moments. It depends on your choice and what you want to do. I chose to do moments about 2 points here, and then sum of forces in one direction. But I can also do moments about 1 point and then sum of forces in X and Y, and then use a system of equations to solve for it. And then lastly, we come to the method of joints at A and D. This is the regular stuff, sum of forces in X and Y directions for both of these, coordinate system put together for all of them, and then these are the results. All right, I hope this was a useful exercise for all of us. Please take care of yourselves and have a great day. Bye bye.